That's much better now.
Test. Alright, now just click on it and then click on it and try to there we go. Okay, nice. Okay, so hello, welcome to my TED Talk. So this presentation is going to be about 101 ways to escape Python jails, and to clarify, Python jails are actually no, you know what? No, next slide. In this case, we'll start with our scenario and then I'll define what a Python jail is first. So first things first is that we want to imagine we want to, as a software developer, create a calculator as a service. So like we want to be able to connect to, maybe it's like an online website or something, and we want to connect to it and do some regular calculator things. Maybe we even want to allow some like Pythonic syntax triggers, such as like assigning variables and printing values. But we're lazy. We don't want to parse it all out. We don't want to, I don't know, try to traverse the AST to try to like calculate everything. So let's just use exec. Next slide. So so in this presentation, you guys will be the attackers, and your goal is to execute system commands, whether that be on Windows, Linux, or Mac. In this case, we'll focus on Linux, and we'll try to execute who am I, which will return CSC Alt Tab. And also to first just preface, Python jails are essentially just what we're trying to do. We're trying to get certain undefined behavior or bad behavior running on a system which is designed to run only like something like a calculator. Next slide. So here's our first iteration. We just have a while loop taking an input and then running exec. Does anybody have? Okay, yes.
Import OS system something.
Yes. Next slide. So essentially, we just run import OS and do os.system. Cool. Next slide. Okay. Well, if we run that in Python 3, it works all fine. But if we run that in Python 2, something peculiar is that errors out on input. So next slide. If we actually just try running this in a REPL, we see that if we just try to print out whatever we input, if we do 1 plus 1, it actually returns 2. And so what that means is it actually executes our input before returning it as a string. Yes, I know. So question is now, back to this in Python 3, how do we prevent this? Next one. We actually just create a blacklist. So in this case, these are just keywords that we're going to try to block. Anybody have the next way for this? No? Okay, next slide. So in this case, we can use eval and exec. So eval will actually return the value of your expression. In this case, we're just doing import os.system, but changing it to lowercase to bypass the restriction, and then we're passing it to exec. So, okay, let's try version number 3. So in this case, the only difference is that we added a dot lower, so that no matter if it's uppercase or lowercase, you can't get past it. Anybody have any ideas after this?
Build the word by like doing int plus 4 and then o plus s and so on.
Okay, but those can only, you can only concatenate those as strings.
Yeah, but like you can run eval, right? So
oh yeah, you could actually run eval. Yeah, that's one way to do it. Next slide. Instead, we're actually going to be thinking about something different. So what exactly does exec do? Well, in this case, exec, by definition, exec is a function that supports dynamic execution of Python code. And one other thing that it also does is that it changes the global state of whatever you're running. So in this case, you set 1 to A, and you print A, it becomes 1. So in this case, we just remove the blacklist. and then we just execute it the same way as we normally do. Okay, let's try this. Let's just try this the fourth time. We have exec, eval, and blacklist added to our blacklist, and yeah, that's it. Any ideas now?
So right now you have a variable word in the local scope. Mm-hmm. Can you mutate the? Never mind.
Okay. Yep.
Well, this is really stupid. But what if you like write into a C file using
No. Instead, we're actually going to be learning a little bit about some metadata stuff. So, yes, thank you. So let's learn about dunder methods, or what they are called double underscore. So in this case, we have certain dunder methods such as dunder class, dunder basis, and dunder subclasses. For a given object, you can use dunder class to access the class that it's created from, and dunder basis to access essentially the parent that it inherits from, and dunder subclasses to access any subclasses that inherits this class. Next slide. And so in this case, we can start with a tuple. Since that is an object, we can use dot class to get the tuple class. We can use dot basis to get its parent, which would be object. And then we can use dot subclass to get everything that inherits from this object class. And next slide. One of these that includes it is this class called os dot underscore wrap underscore close. Next class? Sorry, next slide. So, essentially, we can use what we had before and use dunder init to get to a function inside the context of the OS module, and use .globals to access everything inside the OS module. In this case, we can then use system and who am I? Yes, your director using string concatenation to bypass that. Next slide. Okay, so this doesn't really work. Well, let's just try removing all the ASCII characters, all alphabets. And does anybody have a new idea? No? Okay. Well, let me introduce you to some Unicode stuff. So this is not actually bolded on like Google Slides. This is actually just Unicode characters that happen to be bolded, and for some reason Python 3 executes it. Next slide. So we just try to run it the same way as before. It doesn't actually work, and I have no idea why. But if you run this like with normal ASCII characters, it does work. Somebody can figure it out. Yes.
Is the semicolon also Unicode? Maybe the semicolon needs to be like an ASCII.
Oh, you actually made me right. Anyways, next slide. So, but it doesn't matter. We can use another dunder function called dunder import, which just allows us to import any module and just access any functions from there. Sorry, yes, and also this is actually a valuable solution for the first calculator on Python 2. So in this case, we can actually just run this. Like we can just try it out on our Python 3 REPL and see it works. And if we actually try to run it on the calculator, it actually doesn't work because we have the string OS and who am I, which are both ASCII. Does anybody have any idea to bypass this? Yes.
Can we like declare a byte array and then manually set that and then cast out the string?
The problem is this, to declare a byte array, you either need to use the words like byte array or the letter B.
Not true.
Yeah?
What if you write them out as integers and then you do like an integer char?
Problem is that converting from integers to strings would require the keyword char, like CHR, which are ASCII.
Oh wait, never mind. This doesn't work either. I was going to say hex literals, but then you need X. Never mind.
Oh, you're really close though.
Could you like somehow bring the Unicode inside of the string? Maybe like using eval or something?
Oh, perhaps. Yeah, you can probably actually use eval to just bypass all of this, but you were really close with hexadecimal characters. It's octal characters instead. In this case, we can use octal because it's just straight up numbers. This results to OS, this results to UMI. Yeah. Okay, next slide. Okay, so let's just play a little bit of like, let's just do some review. Which of these default functions in Python are actually vulnerable for you executing system commands? No. Well, okay, I'll get rid of some of the easy ones. You got exec and eval.
Yeah.
Yep.
Import.
Import. Yep. That's vulnerable. Okay.
I feel
Well,
like dirt.
dir. Yes, you can actually use that as like a tool to help you get it.
After like you can delete attributes and not supposed to add.
Sorry, delete what?
Like the first one on the D, like del attribute.
Del adder.
Oh, del adder. I have seen it before. Okay, but probably one of the more important ones are breakpoint and help. for breakpoint, it'll just stop your code. It'll just stop executing your code inside Python, and then it'll open up like this menu where you can actually just execute system commands in it. It's the same thing for help. Essentially, it'll open up something similar to like a man page, and you can execute system commands inside that. So now let's go into like my favorite topic. So who has heard of the anti-gravity module? Yep. Okay. Cool. So if you never heard of it, it's based on this SKCD comic, and if you actually try to import the anti-gravity module in Python, it'll open up a browser linking to this comic on the page. So let's go into our next calculator. In this case, we have a lot more restrictions. We remove get, adder, eval, exec, breakpoint, lambda, and help. So like no cheeses. And we also have a bunch of special characters removed. And we'll just get straight into the next slide. Looking into the anti-gravity module, this is actually what the code is. It imports a web browser, hashlib, and opens up the XKCD comic. So looking into the web browser module, what actually happens is when you do .open, it'll call register standard browsers. And inside there, there is a case where if you have the browser keyword defined in your environment variables, it'll use that to try to open up the browser. Next slide. So in this case, this is how you actually exploit it. So to break it down, what happens is that first it'll import the OS module, get the environment variable, and set it to this dictionary of browser equals bin sh -c who am I. So once this environment variable is set, it'll import anti-gravity. And then what will happen is when you import anti-gravity, it will import the web browser module, which will run this command as shown below. Okay, so none of these work. Instead of trying to do this ourselves by like using strings and just check it or occurrences in a list, how about we try using like something actually more Pythonic, like I don't know, the abstract syntax tree module. So this just allows us to kind of break down the code and parse it and break down the code and parse it and maybe make it more manageable for us to find badly behaving code. So in this case, as an example, we have a is equal to 1 plus 1 and we print a. And if we use ast.parse and ast.walk, it will allow us to print out all the opcodes relating to these two instructions. Additionally, we can actually use compile, which we'll be using later. So this is a actual challenge from a competition called Google CDF. And in this challenge, you are able to take an input, compile it, and it will call this verify secure function, which goes through all your opcodes. And if you have a import from or call opcode, it'll just deny it. So next slide. This is now where you guys can win some money. I got $5. I got $5 in my hand, and if anybody can come up with the if anybody can come up with a viable solution to this, they get the $5.
Can you go back a slide?
Yeah.
Yeah.
Just to clarify, this is like still just the equivalent of AST.parse.
If you want to try and give an input that will execute.
This is like who am I? Yeah.
Yeah.
What is AST.call?
AST.walk.
Dot call.
Oh, AST.call. So like it's a function call. Like imagine you had like exec
Okay.
and like a function and like the brackets would be a
Okay,
function
yeah.
call. Yeah.
What's the source code for the OS system module? Can you just like spat out the whole thing there?
You want to spit out the entire OSL system module.
Well, not like there's a piece of source code in there that actually runs. Oh, it's all written C. That might do it.
Here, I'll give you a hint. It uses some Dunder methods. If you ever had to create your own kind of class with some Dunder methods, this it will apply to here. No?
Wait,
Oh.
The exact thing that we saw earlier where we could like go to like
the base class, go to 127 and then use it. What if, like that has one function call in it, right? And so what if we create like a subclass and that function call we put an add property decorator on. And so then accessing that is no longer a function call, it's a property set.
That's actually pretty close, yes.
We call type on X. What if we just change, the type is defined by dunder method, and so what if you change the type dunder method on X?
That's also kind of viable, but no, sorry. Actually no, here you can't really do it because type is executed before before it executes your code.
Oh,
Okay, whatever. Decorators are the closest. Next slide. Yep. So here are 5 different ways to actually solve it. So the first one, we modify the os.environ dunder method contain to point to os.system. And what happens is when you actually, what actually happens inside Python is when you do like string is in whatever, it'll internally call dunder contains as a function call. So in this case, it'll like execute os.system cat flag. That's not actually what we want, but yeah. And there's also like, you can use get item with eval. Here we can use breakpoint. So in this case, when you use dunder stir and you have as a format string, it'll internally call dunder stir. My favorite is this one, which is sys.str.flush equals breakpoint, where if you go back to slides, you actually see down here, it actually prints out whatever you execute. So whenever you're finished executing your code, it prints it out and calls sys.str.flush, which in turn calls breakpoint. And the last one is decorators. In this case, it uses os.system and it uses like, I'm honestly not kind of bad at decorators, but yes. Next slide. And, sorry, next slide. And yeah, that's really it. Here's some links to like all the resources that I used. No, not really all of them, but yeah. And thank you. Anybody got questions? Yeah.
So in Python, I think it's 3.9 or 3.7, there's a function called eval save, which dodges almost all the problems that you can.
Eval what?
Eval underscore save.
Eval underscore save.
Yeah, it's one of the new APIs that dodges the problem that you just mentioned.
Ooh, I don't remember. I don't actually know about that one. I think it might be a Sage built-in.
It's one of the new APIs.
Oh, I see. Okay. Anybody else? Nope. Okay.
Hopefully everyone can hear me. So yeah, my talk will be on pairing functions. Next slide. So yeah, if you're already a math genius, you don't really need to know like half my talk, so you can like skip to the second half. But I just figured I'd like put some set theory in just to make sure like everyone's on the same track. So yeah, so there's some basic set theory. So basically, sets are collections of objects. So we have like 3 sets here. One's a finite set, and then you have the set of integers as well as a set of real numbers. And we define this notation where you put like these straight lines around S to be the size of set S. Next. Yeah, so how do we show when some of these sets are the same size or if they're not the same size? So one way we can obviously do this is counting them. So this only works for finite sets though. So how do we do this in non-finite sets? Okay. Next. Yeah, so basically that's the idea of bijection proofs. So the goal is to basically just find some function that will take an element in our domain and map that to some unique element in our codomain. And so if we can do this, then we say that there exists a bijection between the 2 sets. And yeah, so one way that we can do this is sort of just find this function that in itself is bijective between the two domains. Next. Yeah, so I gave like a really basic example here. These are finite. But does anybody want to give like just a function that would map from like W to D or from D back to W? Sure.
F of A is Z, F of B is Y, F of C is X.
Sure, yeah, perfect. So if we go next, yeah, I gave some examples. So one of them is just mapping A to Z, B to Y, C to X, and then, yeah, the inverse mapping as well. Next. So here's like a bit of a more fun examples with non-finite sets. So one, we have the set of even natural numbers, and the other one is we have the set of odd natural numbers. So does anybody have an idea? Or does anybody want to take a stab at it? Yeah, sure. Yeah. Yeah.
Just add one and subtract.
Sure. Yeah, that works. Exactly. All right, go next. Yeah. So basically, our mapping from our even to our odd numbers, we just subtract one, and then if you go next, yeah. So our inverse will just be just add that number back. Yeah, perfect. So yeah, now let's say we already did the mapping to show that the number of odd numbers and even numbers are the same. So that should have been no surprise to you. Obviously, for every odd number, there's just the even number is just one more. Well, here let's add a new set. We're just with the natural numbers. So if we go one more. So can we find a bijection between the even numbers and the natural numbers? Yeah, sure.
Divide by 2.
Yeah, perfect. Yeah, so if we go one more. Yeah, so basically, as our friend suggested, we just take our even number, and then we divide by 2. So we just get some number in the natural numbers. So, sorry. Yeah.
Wouldn't you need to subtract by 1 after? Because the first one you don't include 0, so therefore you imply the naturals include 0. And so if you divide by 2, you're not going to have that. 0 is
Oh, I'm excluding 0 from this too.
Oh.
Yeah, I mean, I thought I specified. Yeah, I should have specified as well. I'm not a. I like natural numbers without 0 in it. It has an extra problem. Yeah, the few math people will disagree, but like this is how I like it. Yeah. So next. So yeah, now let's say we want to take a bijection from our odd numbers to our natural numbers. So a hint is that we sort of already did some of the work for us. We have this sort of function f inverse that sort of maps our odd numbers directly to our even numbers. So does anybody have an idea for this one? Sure.
2 plus 1 divided by 2.
Sure, that works, yeah. So the idea is basically just to take, like, we've already defined these functions, these bijections already. So we already have sort of the odd to even. So odd to even, we basically apply this f inverse. And then after that, we just apply g. So basically the same thing. Yeah. Okay. Yeah, so something interesting of note, I guess if you already know math, this is not a surprise to you, but our set of even numbers and our set of odd numbers and just all of the set of natural numbers are apparently the exact same size. So yeah, that's the janky properties of non-finite sets. All right, so I gave like this cool visual motivation. So there's one example of maps the open interval from 0 to 1 to the real numbers. So there you go, open that up. Cool, yeah. So we can see that basically we have, so this semicircle basically represents the open interval from 0 to 1. So I kind of shifted a bit to make it a bit easier on my calculations. But this is negative 0.5, which will correspond to 0, and this will be positive 0.5, which will correspond to 1. So if you press play on the T, you can sort of see that you just basically just take this point on the semicircle and sort of just figure out what its image is under passing through this origin point. You can see that eventually, for all these points on this semicircle, it will map to some real number along the number line. Cool, yeah. All right, so now, okay, you got a sneak peek at the next couple slides. But okay, yeah, next. So yeah, that naturally brings us into pairing functions. So pairing functions are, yeah, next. Yeah, so basically our pairing functions are these bijective functions that we just talked about, but the special property is that they map from these sort of vectors or these pairs of natural numbers back to natural numbers. And so one really nice property about them is that they're invertible. So famously, I think like one of the earliest pairing functions that existed is this Cantor pairing function. So we define like pi of k1, k2 to be this thing. And so what's really cool is that it also preserves this monotonicity. So if we take sort of two vectors, k1, k2, and then k1 prime, k2 prime, if there's like a strict ordering on these vectors, this Cantor pairing function will also keep that monotonicity. Yeah, next. So this is just for your reference. This is pretty much useless. It's just like to show that there's an inverse. So yeah, this is the inverse. It's not very trivial, just because it's kind of janky because there's like multiplication and somehow you've introduced square roots and a floor when calculating the inverse back to a real vector. But yeah, just to show it exists. If you're curious, you can always just search this up. If you look at like inverses of Cantor functions, you can definitely just find this. Right, next. Cool. Yeah, so now we saw that we can sort of take this pair of natural numbers and sort of compress that down to one natural number. So naturally, we want to sort of take a vector of n natural numbers and compress that back down to a single natural number. And so we can just do that by just applying our pi function multiple times. So we'll basically have our pi, we'll basically call a bunch of Cantor functions, and we'll compress down our kn element into like some one number. And so what will end up happening, we'll sort of take this n vector and just compress it down to a single natural number. So yeah, as a nice result, we can sort of reduce these vectors down to a single number. Although the caveat is this number will become very big. And if you've seen like the illustration on the last slide, you can see that sort of the points are, or like the path that it takes is through each diagonal, and so eventually it becomes arbitrarily large. Oh, sorry, I have the last part. Yeah, so also a nice property is that since they also preserve monotonicity, we can also like compare these values. So if we take this sort of mapping, where we map this arbitrary natural vector back to natural numbers, we can compare, or we can sort of compare these numbers to sort of see any possible properties in terms of ordering of these original n size vectors. Cool, yes. So here's like some of the use cases. So one really nice use case is multi-message encryption. So if you've done like any cryptography, the idea of cryptography is sort of you want to encrypt these messages and send them on some public channel. And we don't want this we don't want this message to be known by anybody that's eavesdropping on our public channel. And so one really nice way that we can sort of combine messages is using this Cantor function. So basically, the idea is they'll sort of take a bunch of these messages that you want to send at once, and they'll end up just calculating like these ASCII values, and you can sort of compress these down to a single value, and then send the encrypted value over. And so decryption will work the same way. So if you've done like any cryptography, you'll know that you sort of have like this decryption key, which will basically decrypt that value, and then you can reapply the inverse of the Cantor function to get back your original two messages. So yeah, the main idea is basically when you have pairing functions, you can take these blocks of messages and then you can sort of like compress them down. And it's also invertible, which is really nice. So I also linked the paper down there if you're like really interested. Yeah, they like talk about it in like a lot more detail. You do need like a bit of cryptography knowledge just to like figure out what exactly they're trying to say. But I think like for the general public, this is like a good introduction to what it is. All right, cool. So one other nice use case is ML compression. So a nice use case is if we have like some data set that we want to sort of predict something on, but we're not really sure like what we want to predict. A really cool idea that was explored in one of the papers, I don't think I linked it, but a cool idea that they showed on one of the papers is that you can sort of take multiple, I guess, variables that you want to predict on, and then combine them using this Cantor function. And so what ends up happening is you'll take your input, you'll pass your input through a black box model, and then you'll get like some combined output corresponding to whatever, or your multiple outputs that you want to predict. And then you can just apply your inverse Cantor function to get back your output. So this output will basically just be like a vector of like all the things that you wanted to predict. So it's sort of like an all-in-one encompassing model. You can sort of like predict like these like series of variables. Yeah, okay. Cool. And so I think the last part that I want to talk about is like some nice extensions to integers and real numbers. So for integers, they're also the same size as natural numbers. I'm not going to prove that, but just take it for face value. So the way to sort of like compress that is, so let's say you assume that this is sort of the like Cartesian plane, and so basically you apply this sort of like spiral technique. So you map in a spiral down. And you can see, hopefully you can see that like eventually you'll hit every single integer point using that method. And so there's also a way to do this with real vectors. So there's actually like a really nice way to sort of compress vectors of real numbers, or at least pairs of real numbers, back down to like one single real number. So the idea is to sort of apply like an interweaving technique. It doesn't actually, like it's a bit more complicated. I'm just going to give like a really brief introduction to it. But the idea is basically you want to interweave digits of your number, and that will generate like a unique real number. So yeah, I think that's it. Yeah, and that's it for my talk.
everyone can hear me right now. So hi, I'm Navya. I study CFM, and I'm here to talk about like challenges with deep learning at scale, especially when you factor in like hardware constraints that come with like the kind of explosion we've had in model size over the last few years. So some amount of context on what sizes we're talking about, right? We went from something that was like a Fritz 3, that was state-of-the-art chess back in 1997, ran on one CPU. We went from that to something like AlphaGo Zero that ran on like pods of 64 GPUs for like days at end for training as well as inference time. And or we look at like something like GPT-2, which was trained on about like a corpus of 10 billion tokens taken from the public internet. And we went from that to GPT-3 that was about like 410 billion tokens, or 175 billion parameter model, about like 100 times growth in the number of parameters we're talking about. And what this means is that we're seeing two types of explosions. We're seeing explosions in the number of trainable parameters, and so just the number of values that like we learn via backpropagation over the training process. And why is this important? This is important because, well, it lengthens the training process. The amount of data that's actually used as input to these models. Why is this relevant? Because originally a lot of gains were made by like creating new architectures, right? We went from the time of like AlexNet, we went from there to like the introduction of the transformer. And these were fundamental architecture upgrades to how a lot of these like models were built. And when you have deeper architectures, you tend to need more and more data for like your training process to converge. And therefore, the amount of compute that's needed at train time just keeps exponentially increasing. This also hurts your inference time because the higher number of trainable parameters you have is the higher number of like MAC operations you need to do at inference time. A MAC is a multiply, addition, accumulation, which is essentially the operation that powers matrix multiplications on your GPUs. And higher the number of parameters, higher the number of MACs, slower your inference time will be. And therefore, we see this exponential rise in the size of these models. And historically, it has not been an issue, mainly because we assume that Moore's law holds. What Moore's law tells you is that the number of transistors on your chip is going to double. It used to be every year, and then they were like, oh no, we adjusted the law, it's every 2 years. But regardless, the point being that we had the hardware to be able to keep up with this. Next slide, please. What we recently ran into is the idea that maybe we don't have that hardware. Why? Because we reach transistors that are a few nanometers wide. And when you reach that scale, you cannot go further without causing electrical leakage. What is this electrical leakage? Well, electrons just decide to, well, not be where they're supposed to be. And if that happens, your inference is no longer accurate. You're forced to reduce your voltage in order to not cause electrical leakage, and any gain you got from like smaller transistors is wiped out. And so what has this really manifested in? You can see NVIDIA GPUs over the last 4 years, the amount of memory in these models. Why is memory important? The size of your weight matrices, number of trainable parameters, etc. That has increased maybe 20-25%. The amount of like flops, which is like the floating point operations per second they support, has also probably increased like 60-70%, while your models have grown like 100x. And so that is the major point of difference. That means that we have issues running these state-of-the-art models in production. And so what really is latency? Latency is like the maximum between the time it takes you to compute, which is your computational bandwidth. That's a function of like your floating point operations per second. And the amount of time it takes you to move things in memory. What do you really need to move? You need to move your weight matrices because, well, I actually have to perform matrix multiplications with them. And I need to move my activations, which is like the result of those matrix multiplications. I'll probably apply like a ReLU, a leaky ReLU, etc. at like every layer in my model. And so all of these need to be moved. So if you have something like AlexNet, for example, we're going back in 2012, 61 million parameters. If you represent each of them as like 32 bits, like let's assume we're not dealing with a full 62-bit representation. We're still dealing with about 232 MB of data that has to be present in GPU memory of like whatever GPU you're using at inference. Now scale that up 100 times and you start realizing how before you ever run into computational bandwidth, you're going to run into your memory bandwidth issues. Because even if your GPU or your device could theoretically support those number of floating point operations, you just can't hold all the data you need in memory. And often it's the case that your activations become a stronger limiting factor. Because how do you calculate activations, right? The peak activation in a model is the sum of input activations and output activations. So what is your input activation? Think about it as every possible value in my input. So when I'm dealing with like a convolution, that'll be my batch times channel times height times width, and same thing in my output. And the sum of them is essentially what is like my major bottleneck, like what is the maximum amount of activation that needs to be dealt with at one layer in my model. And it's the peak that's of interest, not your maximum, because like your bottleneck is always your peak. And so how do we, and the notion of activation is closely linked to the number of multiply accumulate operations. I'm multiplying two matrices together. One of them is a m by n, one of them is an n by k. The most naive way to do this is go through like everything here, go through everything here, that gives me one value. Which means the total number of MAC operations I'm doing is m times n times k in like a very general matrix multiplication sense. And we can use that to essentially infer how the number of MACs change for different types of layers. Your linear layer is pretty simple, right? Like I have these many input channels, I have these many output channels, combine them together, hey, I know what my MACs are. Gets far more expensive for convolutions because now you have input channels and output channels to deal with, and like kernels become big and so on and so forth. The point we are essentially trying to make here is that every new innovation that was ever made in like, hey, we have this radically new architecture called transformers that's going to change the world, we burdened our hardware. Because every new layer you add, the number of MAC operations rises exponentially. So yeah, what does this mean? Well, you can't run like state-of-the-art machine learning real time. If you ran like ChatGPT, for example, at the scale that Google search runs, well, it already emits something like 25 tons of CO2 a day. And so why can't we do it? Three things: latency, memory, energy. Energy, you can obviously see atrocious amounts. Memory, it takes about 800 GPUs to hold a single like ChatGPT model in memory, which means you're going to have to run this parallelly across massive nodes. And lastly, just cost. It already costs about like 100,000 a day to run ChatGPT at the scale it does. Scale that up to the number of queries Google handles, that would be more than 6 billion that it costs just to run the LLM for a year. Next one. So, like, what does this really mean? And I was hoping to use like a case study from something that like I personally worked with over the last couple years. So, some context. Since like third year in uni, I was working part-time as an engineer at a startup in Toronto called Wombo AI. And what it really does is it's like a generative AI tool. The idea being, can we create like a creator experience, everything from like customizations, everything from like very granular mask-based edits, style-based designs, etc., for people to interact as finely as possible with art generating models. And we had to build out like an entire async runtime. What that really means is, how do we allow people to send requests that actually hit these machine learning models? And we need to do this to handle it at scale, right? Because you're essentially a consumer social app. You're not planning for your medians, you're planning for your tails. Like, I want to be able to handle 10x my current traffic because if I go viral, I want to be able to handle that. And so some of the interesting problems we ran into when designing this is, this system for context has handled something like 1.4 billion generations over the last year and a half. Operates at something like a 300 query per second on like our GPU pool. And what we run is a combination of like BQGAN, which is like an older art model from like 2019, and Stable Diffusion, which you would probably have heard quite newer and nicer and better. One of the main problems that we have is you take a vanilla Stable Diffusion out from like the repo, from the research lab it came out from, you slap it onto a bad boy GPU. It's probably going to take like 8 seconds to get an end-to-end inference on a fairly reasonable, like, I don't know, like 1500 by 2000 aspect ratio. That's essentially the kind of aspect ratio for a image you would want to share on a Twitter, for example. And those kind of runtimes are not acceptable to us, mainly because like at that scale, 8 seconds per generation is outrageously expensive. And that means we have to have like hundreds of GPUs out there. And this was like one of the main hardware constraints. Like even the best GPU out there, like, okay, A100s are too expensive, we won't consider them. Even V100s, the second best GPUs out there, they take a lot of time to run these models. And so how do we actually get around them? And we worked on like a large number of optimizations. Some of them panned out and we were like, yay, and some of them did not. Some of the ones that did was the idea that when we design for inference, like cache hotness matters a lot. And what this really means is that your first inference will likely be up to 10, 20x slower than future inferences because memory locality matters on a GPU. And when you do these inferences, the GPU will move these weight matrices to places where it will be faster to access in the future. And so the first ever stable diffusion inference on a V100 would probably take like 7 seconds. Later ones we can ensure take fewer time if we ensure that those stable diffusion weight matrices stay in GPU memory. And this is a challenge if you're hosting like a wide range of models, right? Like I have like 7 different models I'm hosting. Maybe I'm even allowing users to create custom checkpoints. And at any time if my model goes out of like the good places in memory, I incur that cost of getting them back there. And so some of the most interesting stuff we had to do was actually build special scheduling heuristics. Like I want to ensure that some GPUs always have some models very hot in cache. And that is hard if I have a large number of models because I have no prediction of like, hey, how many requests will come for each model type. And so a lot of work then goes into like, hey, how much is my GPU memory? How many models can it hold in its maximum? Maybe it can hold 6, 7 models. Maybe I split up my entire, like if I'm hosting 40 models, I know a GPU can hold 6 of them. I'll split my 40 models into say groups of 6 or 7 sets, each of them having 6 models. And when I split that, I will create one node cluster for each of those sets. And so what I'm essentially doing is I'm reducing my problem set from like 40 to the number of groups I have. And so I can then split my inference request to whatever node group is actually holding my model and allow each of these groups to scale independently. And so at no point is a GPU now trying to figure out which 6 of the 40 models should I hold in memory. It will hold all 6 of its models in memory. And instead I'm actually scaling up the entire size of these GPU clusters. And so these are some of like the scheduling heuristics that you end up playing with, how predictive your auto scaling can be, because you don't want to scale when an inference request comes in, because obviously you take time to like heat up things in cache, spin up, provision GPUs, etc. How predictive can you be in how early you provision things? Some other very interesting stuff you can do is like hardware specific compilation, where you compile your model to a particular T4 or a particular G5 or a particular like GPU that's of interest to you. What that compilation actually does is that it'll leverage like lower level like CUDA operations that will not be leveraged if you run like a general like a PyTorch model, for example. And that can give you like orders of magnitude speed up compared to like running a torch script. You can also, as I said, peak activations. That's your major bottleneck, right? Like what is your input and output activations. You can actually go through your model, find a couple layers that are like the most problematic. In our case, it was like the middle iterations of stable diffusion, where it's like still fine tuning the details that had a massive amount of activations. You can essentially play around with this by reducing it on both sides. Think about it this way. I reduce the size of my image. I apply multiple layers of stable diffusion. So number of activations is still low because my image is pretty small. I go through like the most like hard or like largest parts of the model, and then I upscale before going through the final set of the model. And what I'm essentially doing is that I'm trying to be at that upscaled version for as many layers as possible, because that's where I get my details. But I try to be at the smaller size in the starting bits of the model because I'm saving on the number of activations. Allows me to run orders of magnitude faster. Because the idea here is not to get the correct output. These are generative models. It's to get as good output as possible with as little compute as possible. And yeah, you can like parallelize business processes in the sense that mostly when you get GPUs, you get 4 CPU cores attached to them. That's like the most basic configuration you get. Max out things running on your CPUs. There are some very, very annoying things with like the Python global interpreter lock. I would not get into that, but it is a cause of much pain. That makes this a little bit harder, but it is nice. And you can always like use mixed precision, train on like floating point 16s, because remember when we did like what's the size of a model? It depends on the number of bits used to represent each value. The moment you go from like FP32 to FP16, you're cutting that down in half. You go down to like int8 models, you cut that down even further. And so like, but you have to like retrain them because you lose a lot of value if you just directly like round off a trained model. You have to fine tune once you round off. And that's what like mixed precision training really is about. And yes, I will just run through them, but quantization and pruning is one of like the most effective ways you get these models to run faster. Idea being not every data is important, cut out the things that aren't. But how do you figure out what's important? Maybe you're trying to like, because this is a combinatorial explosion problem, right? Like if I try to like cut each one out and be like, oh, how much is my accuracy effective? And so you usually have like a lot of heuristics to play about, because stuff like this is going to explode in parameters. But I can look for patterns. I can look for like, hey, can I eliminate like entire channels? Or hey, is there like specific patterns that I know from like business logic that are going to be the most effective here? And so there are a lot of ways that you can play around with how you want to prune your models. And obviously, the moment you prune, you're going to always get an accuracy hit. But there have been a lot of studies, I'm probably going to link one of them here, where if you prune, fine-tune, you can cut down about like 70% of your model size with negligible effect on performance. And for most of the state-of-the-art models here, I believe this one was based on like an XLM model from Google. But as you can see, like the effect of pruning, you're cutting down your max by like 6 times. That's like literally a 6x speed up on your model with like very negligible hits on quality. And yeah, and one of the ways that we, like a second case study that we worked with that I think is very relevant here is like semantic search, where the idea is, hey, I have some art, find me similar art. Similar, very vague, you know, some sense of like aestheticness associated with it. And the way we wanted to do it was embed it into some latent space, find close by vectors. And there's something called clip by OpenAI that's like very useful here, where you take some text, you can embed it, you take some image, you can embed it. Text that looks like the image will be close by, and that allows you to do like semantic search very efficiently. But like designing this to serve like a very high QPS is hard, because when we estimated it, napkin math, we had to serve something around like 1,000 similarity, like process 1,000 dreams that are similar, or 1,000 artworks that are similar per second. And if we did all of this with like every single one thrown off as a separate operation on a GPU, that was outrageously expensive for us. And so I will skim over the details because I'm running over time, but some interesting things that work out for inference here is in something like this, where do some machine learning model, like run clip to get embeddings, and then fire off to some database to get similarities. One of them is IO bound, one of them is GPU bound, which means that you can get massive amounts of performance gain by parallelizing them. Parallelizing them in the sense that on a GPU, embeddings take like 11 milliseconds. My IO is going to be much higher, so I can create custom GPU specs. I believe that the amount of work that my GPU does 1/4 of the time that a CPU does, or maybe does 1/7 of the time a CPU does, I can get more CPU cores attached to my GPU. What that means is every core will be like, hey, let me get embeddings from the GPU, and then once the GPU is free and can do other stuff, my very cheap CPU can now go and like spin up threads and interact with databases and do whatever I want, and I'm freeing up my GPU. So the idea is like you're not maximizing CPU performance. CPUs are cheap. You're maximizing how much percent time, you're minimizing the amount of time your GPU is idle. And there are a lot of interesting things you can do. We managed to get like similarity search down to like 70 milliseconds, out of which like 15 were actually spent on the GPU. So there's still like a lot of potential to optimize, but the idea is given like some art within 70 milliseconds, we should be able to find say 10 arts that are very similar to it. And last slide, this is just like a very high level, like a very like thought out there. You can use vector DBs to like index, right? Like you can use vector DBs to search, like, hey, what is similar? Can you use them to train? Because if you can, then you no longer need like ChatGPT models that like take 8 GPUs to store. Because what if instead of actually storing your weights as matrices on the GPU, they're actually vectors in a vector DB. And when you train, you can differentiate these vectors. Like the idea is like your database actually supports backpropagation. And when that happens, you no longer have to retrain from scratch, you no longer have to fetch weights from some BitTorrent on Facebook Llama that someone leaked, because hey, you can actually go in and customize these vectors, adjust smaller details, explore the latent space, everything, with the idea of it being a database. And there's some really interesting work happening. I know there are a few like YC companies that are stealth in this space, I believe, that are trying to like build a differentiable DB. It's a hard problem. And I believe there is no slide, yes. Thank you.
Does the mic be up? Okay. Good. Okay. Okay. Yeah. So welcome back to Machine Learning Winter 23. Today we'll be welcome back. No, I'm just kidding. I'm not a prof, but so yeah. So today we'll be talking about AlphaGo and artificial intuition. And in the end, so we're going to be looking at how Lee Sedol was defeated by DeepMind, a team of engineers and researchers at DeepMind, and we'll hopefully we'll build up to that system, and at the end we'll have like a quick demo. So, yeah. So first of all, this is like ML, right? So with any ML talk, we need to talk about the different types of ML. So we have supervised learning, which is like the classical kind of like computer vision. You want to predict if a picture is a dog, for example, and usually that will have to be labeled by humans. And then on the other side, we have unsupervised learning, where we don't want to have humans involved with labeling every single picture. So in that case, we won't have labels. So for example, in the picture example, we won't be able to say, these are all dogs, because the machine has no idea what a dog is. But hopefully you can have some idea of, these things are all similar, and then maybe now if we know one of them is a dog, then since we've clustered them into groups, we would know the whole thing is a dog. Or each thing is a dog. But today we'll be looking at reinforcement learning, which is kind of a middle ground between the two. So supervised learning is humans are involved with every label, or labeling everything. Unsupervised is not really any labels. Reinforcement learning is like our agent, like our model will take an action, and then it will get maybe some feedback from the environment. So in our example, in board games, it's like we have, we're playing a game, and then at the end we know if we won or lost. That's like the feedback that the agent gets. So quick definition, so it's this is like Wikipedia definition. It's a machine learning training method based on rewarding desired behaviors and or punishing undesired ones, right? So we have some tasks to solve, and this is, broadly speaking, it's like trial and error. And really, something important to note is that in this definition, there's a built-in iterative approach. So also, Kevin's earlier talked about some iteration on what information we have and then getting new information. If we have any stat 241 takers, this is like the EM algorithm. Basically, there's one number at the end of each round given by some observer. So here's a quick diagram, again from Wikipedia. So we have our agent, it's a robot, and then it will take some action that will modify the environment somehow. And then, so everything needs to go through an interpreter, right? It's like the thing that is sort of simulating the environment in our example. So we have that I, and then the interpreter will say, oh, based on this action, what's the new state of the world? Communicate that back. And then sometimes you'll also get a reward for every step, but in our case, it'll just be at the very end of the game, you get a reward saying +1 if you won, -1 if you lost. So, wait, one thing that you might notice is this is very similar to how a baby might learn. So, in this example, so if this robot were like a baby, okay, and then the interpreter is kind of like its parent, and then that did not have the desired effect I wanted. What is this? There we go. Okay, so we have so we have like some baby, and then it will take an action in its environment. Its environment will change somehow. It'll like go down a slide too quickly or something. Then the dad will say, "Hey, no, don't do that." So in the end, even though it experienced positive reward because going down the slide was fun, it says, "I did not like getting yelled at by my dad, by my angry dad that much." So the overall reward is negative, and then it will learn not to do that again. That was meant to be funnier. So yeah, so basically this is like human learning. It's a bit eerie how similar it is. And quick detour, Daily dose of existential questions. So are we coming up on artificial general intelligence? Well, first of all, that's not a really well-defined question because AGI is like, experts have varying opinions, but generally you need some sort of general reasoning. So what's the canonical example of general reasoning? ChatGPT, right? So I asked the classic example of math to ChatGPT and I said, what is this addition problem? And it gives me this, which looks correct, but I used like a Web 2.0 calculator and I did that plus that minus that and it was not 0. So this is not a correct answer. And then I added 5 words right here. And then it just straight up refused to give me the answer. It says, sorry, I'm an AI language model and I can't solve, it says I cannot solve math problems that involve such large numbers. You can use a calculator to basically like do it yourself, right? So I don't think we're actually that close to AGI, but this is probably a glimpse of what it might look like, at least what we'll build up to. So really quickly, the planning problem is solvable by a lot of reinforcement learning techniques. Basically, you have a state, and then you need to plan in many moves in advance to try and maximize some reward. You can see this is taken from DeepMind. You can see it's like searching through all the possibilities, and then it will have one choice, and then it will search further. It's like searching many steps in advance. First analogy. So today we're gonna restrict our discussion to 2-player zero-sum perfect information games. That's a mouthful. Similarly to how the whole point of reinforcement learning is to restrict the search domain because there's not enough compute power to search the entire space. Okay, so quick history on computers gaming. You probably have heard of this. So in 1997, Deep Blue defeats Garry Kasparov. He's like a pretty good chess player. And then in 2016, that's almost 20 years later, AlphaGo defeats Lee Sedol. AlphaGo by Google DeepMind. Lee Sedol is the world Go champion, was the Go champion at the time. Actually, AlphaGo discouraged him from playing Go, and I think he later stopped playing professionally, largely due to this event. And then today there's Catago, which is started off developed by Jane Street. Now it's open source. It's online. This is Go software that is better than even the version that defeated Lee Sedol, and it's available just online. So like really, this AI is just getting better and better and more accessible for everyone. Yeah. So okay, intuition is a very hard thing to talk about. It's not really. Like, even the best of the best in their field, they just show the quotes, can't really describe sometimes what they're doing. So Garry Kasparov says it's intuition first, then calculation. Magnus Carlsen, another pretty good chess player, says sometimes a move just feels right? So like, there's no explanation for why, or not like an exact explanation. You can obviously back it up by calculation, but you just say it just feels right. So again, the main problem is we want to reduce the search space to a few candidate moves, because if we had infinite compute power, then we could just like search everything in like brute force. You can just do that in like CS 135 or something. But the search space is too big. So what is training in this case? It's honing the machine's intuition to hopefully only consider moves that are likely to become to lead to good positions. And so Deep Blue used alpha-beta pruning, that's a very common thing, but it used heuristics given by humans. So humans would say, and I put this board here for example, if you play chess, you would know that a rook generally is better if it is not blocked by your own pawns. So one of like the 6,000 heuristics that Deep Blue was based off of is that if a rook is behind one of your own pawns, reduce its value slightly. But if a rook is on like an open file, then increase its value slightly. And then at the end you get some valuation for both sides that sums up to 0. And then you can determine which moves, then you can consider all possible next moves and then pick the one that leads to the highest score. But again, I call that cheap intuition because you can describe it so concretely. It must not be like very deep, right? You're just looking at what file a rook occupies, for example. So how can we remove humans from this loop? Because in the end, if humans are involved in the training loop, then the final player will only be able to play as well as a human, at least to some degree. So quick AlphaZero setup, so quick definitions. The agent is the thing we're training to play. The state is the board, possibly with history. So for example, in chess, there's a 50 move with no pawns, means with no pawn moves from both sides is a draw, so we need to maybe know some history. And also we want to know whose turn it is. The policy is something that the AI is trying to learn. So at each state, what action should we take, and what it gives a probability distribution. So for example, in the last slide, maybe moving your rook all the way to the left is like 80% chance the best move. It just gives a probability distribution. The value is how good it is to be in a certain state, and the reward is by definition the thing that agent wants to maximize. In our case, it's the reward function is +1 if you won and -1 if you lost. So if you maximize that, then you're trying to win. So these slides actually, I'll go over to my computer and press Alt Tab. Okay, so I was originally going to I had some slides, but I think there was just one graphic that I thought explained it so well that I consulted a lot while I was working on the project. So AlphaGo, it has 3 main steps. So first, it does self-play. So since we have no training set labeled by humans, and even if we did, it's not what we want because we want to surpass human level. So it creates a training set by playing a lot of games against itself. How does it select each move? It uses something called Monte Carlo tree search. So the main idea here is that we're gonna have a current game state, and then we're going to look at the different actions that we can go to, and how might we get intuition? We can just play games randomly, even though randomly is not a very accurate measure necessarily of whether it's actually good. If we have if this position we play out like 1,000 games completely randomly, and we win 70% of them, and then at this position we only win 50% of them, even though those moves are completely random, we can probably still say that the 70 move win rate is better, right? And we can improve this. We can use heuristics, so we can have a deep blue-like machine play games to the end many times, and then that will give us probably a better estimate. Or actually what AlphaGo Lee did, which is the version that beat Lee Sedol, is they trained an auxiliary network to try and predict pro moves. So you can see there that they use human data to train their model. And then there's a bunch of math that you can use to determine which next actions you want to explore more often. And that's, again, since our main limiting factor is compute power, we need to try and allocate that as efficiently as possible. And then the second part is we retrain the network. So from the self-play games, we have many games and their results. So after let's say the person who moved first won, then the starting position will be labeled as a +1. So it's saying the starting position is a winning position. Then the next position is labeled as -1 because that player lost that game. And then basically every position that the winning player encountered is now labeled as +1, and then the other is a -1. And then if you train on that, then you're kind of saying to the network, make sure you remember what, or at least get some intuition for what the winning and losing positions are. And then finally, there's like a 1v1. So after you train on that data set, you can hit the old and new models, and then if the new one is better, then that's the new model that you use for self-play. So you iterate this many times until it's good enough. Again, it's like the EM algorithm. You're just repeating it over and over again. Yeah, and then I think this is a really good graphic. I had just a bunch of text, but I think that graphic explained it better. So yeah, so I mentioned explore. This is like just a quick note on like a important thing in ML. It's like exploration, exploitation, right? So we have limited compute power. How much of that compute power do we want to use looking at new actions that we haven't looked at versus looking at actions that we've already explored that we know to be pretty good? And usually the idea is that earlier on, the more you want to explore because you have more time to take advantage of that. And this applies in real life too. Like earlier on, you want to try a lot of different things because you have more time to take advantage of something new that you might like that you might not have found if you didn't explore. Oh wait, what happened to this? Yeah, this is like the development of AlphaGo. So the top version is the one that beat least at all. You can see it uses human data, domain knowledge, and known rules, and it only works on Go. So that's like very limited. No concern for no artificial general intelligence concerns yet. But then human data and domain knowledge got removed with AlphaGo 0, and then with Alpha 0. Oh, first of all, so domain knowledge is like, it knows that it's playing Go, right? So one thing that it took advantage of is that in Go you can rotate the board or like reflect the board and it'll be exactly the same game. So it can like augment its data in that way. And then human data, so again with the version that beat least at all, they played many games out till the end to evaluate position using a model that was trained to predict pro moves, so like a pro-like player. But here in AlphaGo 0, instead of playing a lot of games out, which was also kind of computationally expensive, we just evaluated using our current model. That's a detail about I skipped over a bit, but yeah. And then with Alpha 0, it gets rid of that. There's no more domain knowledge, and now it can be applied to chess and shogi. And then Mu 0 is like it's not limited to these kinds of turn-based games anymore. Now it has Atari, which you can kind of view as it's doing one move every frame, but also somehow it's gotten rid of needing to know the rules of the game, which I don't even know how that would work, but that's like the direction we're going, sort of. So there are two problems. So first of all, this is still like a black box. We can't really understand, but I contend that this actually isn't a problem. Like even you see like the best Go players today, sometimes the best explanation they can give is sometimes a move just feels right. So it's not really a problem. In the end, as long as it works, I think obviously explainability is nice, but you can't like ask too much of this. But an actual problem is that there's too much compute power required. Yeah. So this is this talk was inspired by a project that I decided to do starting over the winter break, and my training setup was very malnourished. Let me just Alt Tab again. So it's we have here it says it plays. Oh, by the way, in Alpha, since Google has so much computing power, these three steps are all done in parallel. So instead of playing 25,000 games, mine played like 300 games. And then instead of 2,048 from the last 500,000 games, I think it only played like 2,000 games. So it's like very malnourished. And you can see how like, you can see the entire training process. Although they both took an equal amount of time, they both took 3 days. But I would say Go is probably like slightly harder. Okay, no, it's much harder than Othello. I guess I can give a quick demo. So we have, here's the AI. And okay, there's a Go tab, but it's like really bad. So we'll just stick with 6x6 Othello. So if there are any Othello experts in the room, like please help me, because I haven't beaten this bot in like a few months now. I heard going second is better, so I'll just go second. What should I do?
Start praying.
Right? Okay. I searched up like the optimal starting in 6x6 Othello, and that was found using alpha beta pruning. So it's like it's definitely the best sequence of moves. And actually, so I would be lost without it, but actually so far I believe this is the exact sequence of moves that is the best for both players right now. So the Alpha 0 algorithm with a very malnourished training setup has learned at least the first, how many moves in are we now? Like 11 moves. This is also I think that one is not, but I would only know because I searched up the optimal moves. Yeah, oftentimes it looks like you're about to win. Oh wait, that was not a good move because he gave away the corner. Let me just undo that. I don't know. Okay, well, I actually don't know where this was going, but I'll have this available online afterwards. So yeah, just really quickly, a real-world application is alpha tensor. So in this case, so matrix multiplication is like a really real-world algorithm, right? Okay. Well, I mean, like it's used in a lot of applications. So actually, a little improvement is actually really impactful. And by framing matrix multiplication as like a one-player game, and then playing that game against itself, and trying to optimize or like minimize the number of multiplications required, Alpha 0 was actually able, or alpha tensor, like algorithm similar to alpha 0, was able to improve the fastest known matrix multiplication algorithm just last term. So that's an application that goes beyond games. So in conclusion, for AI, good planning, which is often just tree search, is all about refining your intuition. In many cases, you can't even think about how many states. Like if you have to control a car, for example, not saying that that's going to be an application where this is viable in the near future yet, but the state space might just be too big. So it's all about refining intuition. Artificial intuition is real, but it's not that real yet, as we saw with ChatGPT. And this is my prediction. So quantum computing is on the rise. It's still, apparently the largest number we factored is 21. Like literally the number 21, like the 2-digit number. But it's on the rise. So maybe that with reinforcement learning, we'll be able to play imperfect information games like poker. And then maybe it will destroy cryptography, like learn the key somehow by playing the game against itself. I don't know, but if this is right, we have recorded evidence that I was so yeah, so this is based on a personal project. You can play against it at that link. Don't go yet because right now it's hosted on a backend server where you saw how long it took to compute each move, right? So if there are like 5 people, it'll take 5 times that amount of time. So I'll reduce that down and then you can check it out and then you can see the slides there. Yeah, I think that's it. Thank you.